next speaker, and last but not least, I'm now most honored to introduce Professor Dr. Saddy, Professor of Linguistics in the School of Psychology and Clinical Language Sciences at University of Reading. He is also the director of the Center for Integrative Neuroscience and Neurodynamics. That's CINN, if I'm not mistaken. His areas of interest include typical and atypical language processing and language acquisition, cognitive neurodynamics and neuroscience, analysis and computational modeling of brain signals. His works have always been insightful and original in the field and have inspired a tremendous number of linguists to grow interest in the integration of linguistics into the natural sciences. The title of his talk is The Scaffolding of Thought, Turing's Most Important Lesson. And there he is. Dr. Saddy, please.
Okay, can you see my slides? I just tried to share.
We can see your slide, but we cannot see you.
Ah, that's interesting. Why would I want to turn my camera on?
Okay. All right.
All right, so I'll go back to trying this sharing thing. Sorry for this waste of time. I was so proud of the fact that I'd figured out how to share.
Okay, well, so.
Yeah, there it is. Play. Okay.
Excellent, there we go.
All right, okay, sorry for that drama. Okay, so I've got a lot to live up to. Everyone keeps referring to the good things that I'm going to say. I want to start off with asking the very general question, what is biolinguistics? And I wasn't sure myself, so I asked ChatGPT because that seems to be the appropriate thing to do these days. And what we've got here is a list of things which seems not too bad, right? So biolinguistics is concerned about innateness, the critical period, the neural basis of language, the genetic basis of language, and the evolution of language. And all of these topics we've touched on in some way, shape, or form. I'm going to stick to point 3 that GPT has provided us with. But I'm going to rephrase it slightly by saying, what's the nature of the biological or neurological system that's essential for language, and how do these systems determine the possible nature of language? So I'm really going to be talking about very large picture approaches and leave the technical details to more competent and younger colleagues like Juan. Okay, so this question about the neurology of the system raises a lot of questions. But what we'll reflect on is the relationship between linguistic theory and theories of brain function and organization. And we've had reference to the idea that there are certain oscillations that map to certain types of linguistic functions. And if we take a look at sort of the conventional EEG research, we see that we've got the N400 and the P600, which reflect different aspects of language processing. The N400 reflects semantic integration costs carried out in particular regions of the brain, reflected by the polarity and the temporal and topographic distributions of their components. And the P600 similarly reflects syntactic complexity and the cost of reanalysis, again reflected by polarity, temporal, and topographical distribution. Brain activity in brain-damaged individuals tends to show a loss or weakening of these electrocortical components. So, unsurprisingly, if your brain is damaged, you're not so good at generating a P600 or an N400. So on the basis of that, can we feel secure that there's a correspondence between particular kinds of brain activity and language processing? Well, maybe. If we consider extreme cases, these kind of relationships turn out to be a bit more tenuous than we envision. So in advanced Parkinson's patients, language processing components can be restored by introducing high-frequency stimulation into the thalamus. Now, the thalamus is not typically considered to be any kind of language cortex, but deep brain stimulation, which is a type of therapy used to try and relieve some of the most severe symptoms of Parkinson's disease, returns both physical and cognitive capacities to these unfortunate individuals. As Diego mentioned, we also are familiar with seeing subjects who've had portions of their language cortex damaged or even removed, and they can still exhibit N400 and P600 responses. I want to put in scare quotations the term language cortex, because our understanding of what that means has changed a lot over the years. The language areas of the brain, or areas that become active in the brain when we're processing and using language, is quite distributed, much more broadly than typically described. And then the most extreme case I know about is something called Ramessen's encephalitis. It's a fortunately rare progressive chronic encephalitis, so a kind of inflammation of the brain. It only affects one hemisphere of the brain, and it occurs almost exclusively in children between the ages of 6 to 8. And the only treatment is the surgical removal of the affected hemisphere. So this means that children with left hemisphere involvement have their entire language cortex surgically removed just at the point when they're achieving mastery of their language. These children can regain language. Clearly, their brain responses are not typical because they're missing half of their brain, but in fact, they do, in some cases, develop the ability to, for instance, go to university and function well. In fact, I attended a conference that was run by people with this condition. Moving away from pathologies, if we consider MR research that's looked at language acquisition, bilingualism, we see that exposure to new languages actually materially changes brain morphology. And so initially what happens as you acquire a new language is we get increased gray matter density, basically in frontotemporal regions and also in the cerebellum. This is then followed by strengthening or thickening of the myelination and the white matter pathways in the brain, so deep structures in the brain. And ultimately, the gray matter density actually returns to its baseline level. So it's not simply that you grow extra cortex to handle some more language. You actually restructure the brain in fundamental ways, and the density issue is actually transient. So all of these examples, biology is telling us that the biological system that supports language is not a linear system. Furthermore, the operations or computations that support language aren't necessarily tied to specific physiology. And this is important because it calls into question what we can call the standard Cartesian assumptions as they apply to studying language in the brain. If we embrace the position that language does not exist without human biology, then if there's no reliable correspondence between biology and language, the Cartesian approach to explanation fails. The traditional approach to understanding physical systems is to look for ways in which variability or instability is controlled so that the core determinants of a system can be revealed. And this has been the traditional approach to studying linguistic phenomena and psycholinguistics. We create complex protocols which try to balance multiple factors in order to reduce variability or to convince ourselves that we've controlled for stray influences. Okay, so this brings us to Turing's most important lesson. He had a lot of really good lessons for us. One of them might have been avoid eating apples, but we'll skip over that one. Turing's 1952 paper, The Chemical Basis of Morphogenesis, describes how complex patterns can arise from simple interactions of basic processes. And this is a topic that everybody's kind of pointed to. He described reaction diffusion systems, so chemical systems, in which there's competition between antagonistic mechanisms. So this is a clash system. And he showed how this inherently unstable competition can give rise to regular forms and patterns, such as Fibonacci phyllotaxis, which is something that has been referred to a bit. I'm not going to really spend much time on it. The important lesson is that in biological systems, and actually in some physical systems, it's the instabilities themselves that determine the system. So in fact, our concern with avoiding variability and avoiding unstableness actually is sort of leading ourselves astray. We need to find ways to embrace these instabilities. So Turing's approach to morphogenesis actually has a direct application in our understanding, for instance, of the shape of a neuron. Neurons look like this picture here, and they have kind of a fractal form. And as that fractal property increases, the area of the surface of the neuron tends to be very large compared to the cell volume. This is also a similar explanation for why we have such wiggly bit, why our brain looks the way it does. Anyway, so the fractal properties increase, which allows us to have this high surface area compared to volume. That means that connectivity between neurons can increase. When that happens, we start to have competition for metabolic supply, because the more connectivity you have, the more metabolic resource you need. Eventually, some metabolic resource becomes critical, and not all the synapses can become stable, so they die off, and we know that we see this in the developing brain. And the entropy that the system itself exhibits can reach a maximum when the critical metabolic supply is sufficient to sustain basically only half of the synapses near saturation. So in fact, there is nothing in our genetic code that tells us how to build a neuron that looks like that. It's actually the consequence of these instabilities and these competitions between requirements, right, for increased surface area, increased connectivity, and need for metabolites. So this is where I bring up dynamic frustration. So these examples and much of Turing's insight into morphogenesis is captured by a physical phenomena, which has been we've mentioned before, called spin glasses, and is generalized into the notion of dynamic frustration. And that models competition for limited resources to meet contradictory goals. And dynamic frustration itself generates complex nonlinear systems that in fact have a range of familiar properties. And I think that this is an important observation, right? That dynamic frustration is something that is really a critical aspect of the nature of the biological system that we're dealing with when we're trying to understand the nature of language. So let's take a look in a little more detail. So the concept of dynamic frustration, it comes from physics in the context of the study of spin glasses. These are lattices, these are assemblies of electrons where they have a requirement to go into pairwise anti-alignment. And that means that no two neighboring electrons can have the same spin. They can have spin up or spin down. They can't be the same. This means that in a large system, the electrons have to be changing spin permanently in order to maintain the anti-alignment requirement with its neighbors. And the system as a whole can achieve a single stable state. The system as a whole can't achieve a single stable state, but instead you get multiple variable and local solutions. So you have local minima. So the system is in a permanent state of adaptation. This sounds familiar to us. So a dynamically frustrated system is about the irreconcilable tension between opposing conditions. And in fact, it's been suggested that this is the essence of the complexity of life. And in fact, I think Binder went so far as to saying that this was a definition of what a living system was, and it works pretty well. It allows us to, I think, call certain types of crystalline growth structures alive. But other than that, that's the only real gray area. So this gives us a handle on the nature of the dynamics of life. So this notion of frustration, right? It's not just electrons that have to be anti-aligned. Frustrations can emerge in different kinds of interactions and at different levels of organization. And there's three main kinds of dynamical frustration. Geometric frustration, which talks about the trajectories in dynamical systems. When we talk about a trajectory in a dynamical system, we're actually saying, okay, for a particular state, we can see a transit through the system as a whole. And any dynamical system will have multiple possible transits through it. Think of a pendulum. You've got a weight on a string and you push it. It's going to describe a bunch of arcs. Every one of those you can imagine is a trajectory through this total space that the pendulum describes. So geometrical frustration suggests that we've got systems where you have that are naturally opposing, so cooperative tendencies act globally against local behavior. And then we have this notion, and we'll see that's an important organizational property for the brain. And then we have computational frustration, and this is related to the halting problem, right? If the system becomes more powerful, memory increases, so does the amount of resources necessary to probe, and then ultimately it never stops, or else it crashes and burns. We don't run into computational frustration too much in what we're going to talk about. Diego mentioned this paper by Gollo and Breakspear, which they pointed out that this is a mechanism that allows cortical functions to adapt to a changing environment. So dynamical frustrations contrasts with strong coupling that's found in interacting cortical regions. So in the brain, we see both strong coupling and long-range anti-coupling. We've got synchronization emerging from acting regions, and frustration emerges from local recurrent connectivities, patterns that move across networks, so different subnetworks in the brain. Gollo and Breakspear call these motifs. They use basically 3-node graphs to sort of describe or characterize the motifs. And you have exactly the same kind of geometric frustration that we saw in spin glasses. In particular, these motifs, there's a tendency that neighboring nodes tend to be synchronized out of phase, and this can't be satisfied for all 3 nodes in a local graph, and so then we have a problem. And we have geometrical frustration at the motif level and scale frustration between motifs in cortical interaction. And this we see reinforcing dynamics, which provide stability to the system, and we have the frustrated dynamics, which provide instability or metastability. We see this in the next slide, where we're looking at these sort of principles for brain self-organization. We've got cortical surface, the wrinkly cortical surface, that exhibits synchronous oscillation and traveling waves that move across and through the brain. On a long time scale, we have sensory fields that eventually turn to brown noise, which is kind of structured noise. Because of that, covariance between these connected areas decline with distance, and sensory fields and synchronous fields start to pull apart. We get the opportunity then for Hebbian learning rules to emerge through this tension between these regions, and lateral synaptic connection densities decline. So long-range densities decline, and short-range connectivity is reinforced, and the whole thing is driven by a competitive supply of critical metabolite to the synapses, just as we saw for the neuron itself. So this is an example of these this scale frustration. All right, so now we've talked about brains. It's not only brains. So the same kind of stability and instability tension that we just saw for brain dynamics is true in signal analysis. So a human extracting information from a continuous signal, it has to pull out some kind of segmentation and categorization based on some sort of reinforcement properties that's embedded in the signal. The heuristics of abstraction and categorization have to be flexible enough to accommodate changes in the world. And in extreme conditions, it must allow for revisions of any type of internal model that we may associate with a signal. So that may entail, in fact, resampling. So the challenge of signal analysis, this thing that we do all the time via our sensors in real time, actually introduces another type of dynamical frustration. We've got statistical regularities that have to be consistent enough to allow for generalization over whatever variables we choose, which allows us then to build up something that looks like to operational protocols. But the changes in the world, if they're drastic enough, have to be able to drive us into resampling and revision of these statistical priors in order to be able to respond to changes in the world. So we have to be able to have categories understood not in absolute terms, but actually in terms of the system itself. All right, so we've kind of traipsed through the Turing's lesson, the idea that the instabilities are what actually counts. What we have to say about scaffolding? Well, one of the things that immediately arises when as linguists, when we're looking at this, is the notion of grammaticality itself, right? So we've got a new term here, Sloane's problem. This is my wife, right, who said, why do we have a sense of ungrammaticality at all? And I canvassed my colleagues, and they said, I've never heard anyone ask that question before. So her point is simply that we can have an aversion to eating things. For instance, we don't want to eat tainted meat, and this can be explained by an evolutionary force trying to keep us from poisoning ourselves. But what kind of evolutionary force would pressure us towards a sensitivity to grammaticality? We can learn to play chess, and by convention we'll avoid unpermitted moves, but we don't find it impossible to learn alternatives like 3D chess or four-person chess, both of which are nightmares, by the way. Nor are there possible but unattested chess moves, for instance. So what is grammaticality? Well, that, of course, is a very interesting question all of its own. One of the important things that we've learned over the decades and eons is that there are some things seem to be clearly grammatically impossible. So we have things that are considered hard conditions. Here's 3 examples. Okay, so there's no extraction from conjunctions. So we can't say, what did Juan buy bread and? Nor can we say, and what did Juan buy bread? And we can say Juan bought bread and what, but that only has an echo reading. So it turns out that in no attested language is it possible to extract a conjunct member out of the conjunction itself. You have to be careful that you've got the right kind of structure for the conjunction, right? But anyways, this is really apparently a very hard and fast rule. Another one is there's no 4-place argument structure. There's an interesting and long history of attempting to get adults and adolescents and children and infants to learn new words that have four-place predicates, and nobody does it. So language studies and artificial grammar paradigms have shown that a verb requiring a fourth argument beyond external and to internal is just really not on. In fact, I've done some of that research. And then there's the projection principle, which is kind of an interesting one. So there's no lexical replacement in a derivation. And a good example of this that comes to mind is polarity items. So polarity items are items that gain an interpretation when they are in the correct syntactic or semantic environment. And by definition, right, what these lexical items are things that describe the environment that they want to be in. So how come we're unable to simply correct or understand parse strings like Juan has ever been to Tehran? Right? Given that we know that ever needs to be in the scope of negation or in a monotonically decreasing context or an anti-veridical context, you name it, that should be trivial to just say, oh, you meant to say Juan has never been to Tehran. But in fact, what we get is basic, if we have an interpretation, so the standard response is what? And then, oh, you mean he's always going to Tehran? So ever, even though it wants to be in this environment and comes with that label, basically, and its lexicon, we aren't allowed to just fix it. So the projection principle seems to be another one of these rather hard conditions. It's hard to overcome. So the essence of hard conditions themselves, just the fact that they exist, is evidence of the dynamic and nonlinear properties of our language system. In dynamical terms, hard conditions represent impossible trajectories through the space of the grammar. It's easy to augment linear systems with subroutines that grant the system extra capacity without compromising the linear system itself. But for complex nonlinear systems, adding new capacities or a new subsystem without causing collapse is extremely difficult and will materially change the global system. Understanding our biolinguistic system as a complex nonlinear one also provides an account for why some grammaticality conditions are on a gradient, such as differing sensitivities to subjacency, while others seem to be absolute. The gradient effects are consistent with variations in possible trajectories in association with local minima or space, while hard conditions are trajectories that simply are not available in that space. So the notion of space here is an important one. So we've talked about space, so now we're forced to look at multidimensionality. So we're talking about any type of system, but now here we're talking about complex systems. Dimensionality, it refers to the number of variables or factors that define the behavior of the system. In a biolinguistic system, it's characterized by a lot of interacting components, which can exhibit a wide range of behaviors and interactions that lead to emergent properties. We've heard about that right from the first talk on. And they're not easily predictable from the individual components alone, if at all. And in this context, dimensionality can be understood from different perspectives. So the state-space dimensionality is the space of the complex system. It's the multidimensional space in which all possible states of the system can be represented. Each dimension corresponds to a variable or parameter that influences the behavior of the system. In a high-dimensional state space can make understanding and predicting the behavior of complex systems very challenging due to the so-called the curse of dimensionality. But this type of state space is kind of easy to visualize. Let's go back again to our notion of a pendulum. We've got a string with a weight on the bottom. We take it and we let it go, and it swings back and forth, and it kind of moves around. Okay. Well, the state space of that pendulum is every possible position that the pendulum can occupy. Right? So not just one trajectory, but the infinite possible trajectories that the pendulum allows. its dependent weight to move through. This defines the state space of the pendulum. So if you imagine now you've got a much more complicated system, you'll have a more complicated space. The dimensionality is going to go up with the degrees of freedom. That's the second one. Degrees of freedom, another way of describing the dimensionality of complex systems. It's the number of independent variables that can be changed or manipulated without affecting other variables of the system. So a degree of freedom can be seen as the minimum number of dimensions required to fully describe a system's state or behavior. Keep in mind that the component systems contributing to larger complex systems will themselves have dimensionality. Okay, so we've had a dynamic frustration. Let's introduce dimensional frustration. This is an information theoretic characterization of dynamic frustration. It's tension within a complex system driven by informational packing differences, density of information between components of differing dimensionality that compose the whole system. All right. This actually turns out to be quite an important notion to keep and get in your head around. All right. So dimensional compression is a necessary component of any system that delivers signals via human transducers. Okay. So it's not just reduced, it's not only about humans, but we're concerned about humans. So voice and gesture, let's say. Any given self-similar complex can be multidimensional. The dimensional compression of that system, all right, so you've got something of multiple dimensions and you're going to have to express it with fewer dimensions, okay? It's not going to be smooth. Dimensional compression delivers an imperfect rendering of the information or information structure of a higher order system into a lower dimensional version, and vice versa. A lower dimensional object or system cannot completely fill the space defined by higher dimensional object. And there's some nice math and a bunch of cool things to look at. Cantor's theorem, Hilbert. There's a paper that Juan and I have called Measuring Language. There's another paper called Syntax and Uncertainty. And there's something called the center limit theorem, all of which talk about this business of attempting to get information out of systems of different capacities. This means that there's necessarily a mismatch between the nature and type of information available at different dimensionalities between partners in complex systems. Importantly, the systems will constrain the possible range of mappings. Because the systems themselves define the possible interactions, while there may be variability in the types of mismatches attested, there will be a hard limit on what those can be. And there's going to be an edge beyond which the system cannot venture. Just like the pendulum can't suddenly move to the building next door. All right, so let's think about these ideas. Cognitive and linguistic systems are constantly confronted with this dilemma. Our job as sentient entities is to create high-dimensional models of our world, or possible worlds, based on information that's delivered via low-dimensional input, audition, vision, olfaction, haptics. The decoding of these signals and their subsequent integration creates higher dimensional systems whose informational space is not completely exhausted by the contribution of any of the lower dimensional contributors. Think about building up higher dimensional object of the speech stream. It will always underspecify the information state in the state space. And in fact, you can imagine that what happens is as we build up our complex knowledge of the world, we start creating links between concepts and ideas, which makes that even higher dimension, even though we haven't actually had the speech stream deliver the details of the higher dimension. When we try to act on our higher dimensional models, so we're faced with the need to deliver high dimensional information through low dimensional channels. So we've got a complex model of the world. We want to tell you about it. We've got just our ability to deliver a voice or a gesture, And we've got a whole bunch of information that we want to squeeze into these one types of operations. We're familiar with this phenomena. It's always a challenge in externalizing what we know. So for instance, we know how to ride a bicycle. That engages a very high dimensional system, which we constructed usually in our childhood. While we can demonstrate the act of bicycle riding, explaining it to someone is quite another thing. This disjunction between what we know and what we can actually express is a reflection of what's lost in dimensional compression. We can describe what one does when one rides a bicycle. It's pretty good for setting a goal or describing a situation, but it's totally useless if someone actually wants to learn how to ride a bicycle. Experimentally, we see this in train and test situations. So in the lab, we can train subjects, expose them to stimuli, and they can implicitly learn incredibly complex dependencies. But if you ask them to reproduce what they've learned, right, so behaviorally or their brain images tell us that they've acquired sophisticated information, and now you ask them to actually produce it themselves, they actually return to very simple repetitive behavior, even though we know that they actually know the details. We see this in other types of domains associated with certain types of brain pathologies. For instance, there's something called word blindness, where people can't read, but they can tell you if a word is spelt properly or not. So they have access to information that they can't actually express. Okay, so this gets worse. Okay, so not only is there a reduction in dimensionality, transducing between complex knowledge to communication, there's also a need to deliver the dimensionally reduced information in real time. Right? So usually when you're talking about dimensional compression, you're not really worried about time in these formulas. But in fact, for humans, that's what we actually have to do. Not only do we have to dimensionally compress information, we have to deliver it in an unfolding stream. So this adds further constraints, as it's got to be possible to track dependencies not only in the speech signal itself, but also dependencies that move into these higher dimensional representations. In fact, there's a solution to this, and it's one that we run into all of the time when we look at these dynamically frustrated systems. It's called self-similarity. So dynamically frustrated systems can lead to the formation of complex manifolds. These are surfaces through space in the system with many local minima. And the distribution of the local minima exhibits something called hierarchical or fractal-like structures. And these are characterized by a self-similarity that's manifested in the scaling behavior of correlation functions over different lengths and time scales. So what this basically means is that the signal itself shows similar distributional properties no matter how you look at it. Interestingly, recent research has shown that humans are sensitive to self-similarity. So there's a work from a guy named Martin. There are references are in here somewhere. So in Martin's group, he's shown that their brain responses actually discriminate between changes in additive as opposed to fractal complexities. So you can show people pictures that change, and if they change in an additive way, that is that you just add more components to it, we notice that, right? But if we show them a change that becomes more complicated by increasing a fractal dimension, we react to that in a completely different way. So in terms of contrast, but also in terms of additive. So if you have one thing, a simple schema, and you make it additively more complex, your brain response is of one type. You start with a fractal image and you make that more complex in fractal dimensions, your brain responds in a different way. DeHaen's lab has shown that humans are sensitive to scale-free transitions, And in fact, the Kolmogorov complexity of binary strings, Kolmogorov complexity is a weird one. Its Kolmogorov complexity is actually described as the number of statements necessary in a computing program to generate the binary string that you're looking at. So clearly, we're not reverse engineering the binary string to come up with the answer to the Kolmogorov complexity. But in fact, when we look at humans' behavior, they behave as if, as Diego's as if, they're actually sensitive to Kolmogorov complexity. And then in my own work, we've got evidence supporting high-level representations driven by self-similarity. So when we're exposed to signals that have embedded in them self-similar properties, we build very elaborate hierarchical representations, which actually recapitulate deterministic and non-deterministic distributions that are embedded in the superficial stimulus without there being a perfect mapping between individual elements of that stimuli. So there's very interesting research that shows that self-similarity is a very important aspect of human neural behavior, and it goes through a wide range of phenomena. Okay, so I'm at the end. So what does all this tell us? So our cognition, like our biology, involves complex interactions and tensions between systems of varying dimensionality from both the representational and the derivational perspective. It's therefore not surprising to find similarities between linguistic and physiological entities. So, like Mohammed and Suran had mentioned. This is incompatible with simple computational characterizations, right? This dimensional compression stuff leads us into a nightmare if we are trying to stick with only one type of computational characterization. So this is consistent with what Diego was telling us. And capturing the information caught up in such complexity requires a notion of features and categories that can exist across scales and levels. And I think that this is quite consistent with this work that Juan described and also that Mustafa was talking about. So, final point is, as linguists, our object of study is best thought of as an expression of competing unstable requirements. Language provides a low-dimensional structure for expression of high-dimensional representations, and therefore it's a kind of scaffold for thought. And that's it. Thanks for your attention, and thanks to everybody else who's helped me come up with these crazy ideas. Now, I understand this to be a workshop, which is why I presented it in the way I did. And also, I believe we've got some time left to actually ask questions, not only about what I've had to say, but also from the other presenters as well.
So thanks a lot, Prof. Saddy, for the awesome presentation. It seems we are having some bandwidth problems, so all of the webcams cannot be shown at once. We will appreciate it if you turn off your webcam for a bit so that we can see if we can retrieve the chat box and the list of attendees. Yeah, there it is. Okay, great. And yeah, the chat box.
I'm back. I was.
Yeah, welcome back, Mr. Berzinger. So yeah, it's not stable, so we cannot keep the chat box here. I suggest that we have a round discussion based on what has been discussed, and we're very much looking forward to it. Thank you.
And Dr. Safavi, thank you very much for taking over this. And Douglas, that was just wow. And I'm sorry, I just got kicked out. Maybe that was the dimensionality, kicking the system out for Axiom 12. We don't know. And I guess Skyrim is kind of intelligent because we've been talking about dynamical systems and clashing for quite some time, and it has managed to uh, clash at the end of the story. But yeah, okay, so the chats are back, users are back, things are good again. Okay, the world is beautiful again. So,
So did you hear me complete my
yeah,
presentation?
definitely so. Everything you said, word by word.
All right.
So,
Okay.
okay, so I would love to invite all of you, Dr. Darmagadam, Juan, Douglas, Diego, everybody, to have a random discussion. You can switch on your webcams and let's talk about you and scaffolding with thought. I'll be quiet.
Okay. Where's Diego?
Well, I'm not sure what the protocol is.
Yeah, what? So, this is the very ending. You guys have been waiting for all these questions. I remember you having like billions of them.
Oh no, we often talk. In fact, I'm hoping that this was recorded because this probably will help us finish our book. Now,
Okay, we're gonna have to sell that to you if that's the case.
Yes, that's right.
All right.
Well, so just to kick off the discussion, I mean, you said a lot of important things, Doug, that, as you know, I subscribe. I mean, the idea of having system-driven categories is key. We've been saying that for decades, as opposed to, just listing them independently. They have to be system-driven. Your connection between self-similarity and forms of indexicality or other such issues. As you know, I think that's hugely important as well. I should say, by the way, that CLASH for me is an acronym for Conditions Liberating a Simple Hiatus. In other words, it's not the same as a crash, as in the crash of Wall Street, although of course it's a pun. But the hiatus
pun intended, sir.
That's right. But the thing is, though, that the levels that the clash implies, right? The conditions liberating the hiatus is going to have to be the domain at which you evaluate the dynamical frustration conditions, which, per the reasoning that Doug was pushing, you're probably going to have several situations of frustration because by now we all think that lots of things are involved, right? So acoustics could be involved, gesture could be involved, phonetics, morphology, syntax, predicate semantics, pragmatics. I mean, this is without even going into metaphor or whatever else is necessary, which could be a central part as well. So there's multiple domains which we suspect happen at different times, and clearly also with different parts of the brain being involved. So each of those could pose a problem of compression, dimensional compression, because ultimately this species managed to squeeze this through something like the motor system, which is a massive compression of information. So just laying out the details of that is not going to be trivial. I mean, that's the fun of it. And last point to finish with this, because it keeps puzzling me, is the arbitrariness, right? I mean, so we always go back to Saussurian arbitrariness, and there's a famous discussion he has in the course about, how many things we used to think are motivated or not, which I take all of that directly. However, imagine yourself, you ask the following question. Take Morse code. In Morse code, you have empty space, you have short, and you have long, right? Beep, 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 right? Those kinds of differences. Now, suppose you ask yourself a semiotic question. Is it arbitrary that we choose a long signal to represent, to arbitrarily represent the B code? Could we have turned it around? And surely you could, right? You could imagine that B represents a short bit and bit represents a long bit, sort of reversing the mapping. But intuitively, that seems perverse. And so in what sense is the coding then arbitrary? Or to what extent are we tracking, in that case, just the short versus long in terms of the fact that the signal is long versus short? And I mean that as a question because I'm puzzling over that.
Well, yeah, so this is a much bigger question, right? So you at the very beginning of Juan's talk, he said he was interested in the when of iLanguage, right? And so the question of how does time get into these systems? And it's, time is a very difficult thing to actually capture. There is no time, right? There's this evolution of entropy, right? This tendency towards disorder. But what seems to characterize the systems that we're concerned with is that they're dancing around the sort of maximum entropy values. So disorder is not a particularly good metric for time in these situations. So it seems to me that one of the things that actually we need in order to have, well, let's turn it around. One of the things that we have which allows us to actually use something that we consider to be time is self-similarity, right? So the fact that you can track information back in the signal, right, in a way that is recognizable and dependent on the current state provides us with a way in which we can say, all right, this is something that we would call temporal. And the question, so that's because you asked short versus long. Well, how the hell do we know what's short and what's long if we don't have a sense of time, right? Okay, if we have a sense of time, where does that come from? And how do we actually make use of it? So we have these notions of synchronicity and phase and coupling. And all of these things actually are manifestations of temporal dependencies. Or at least that's one way of thinking about it. And as you guys talked about this trade-off between frequency the different ways of characterizing the dynamics, time seems to be an important aspect that pulls those things together. But
Sure.
But when you actually go and ask, how do we as an organism, how do we as a biological system extract time? It's not clear, right? It's really unclear, and it's not trivial either.
Mm-hmm. Diego, you seem to have deep thoughts about this one. Do you wanna comment?
Big thought is a little bit of an overstatement. I think that an interesting aspect that emerged is the fact that you're concerned with the when, as Doug said, but at the same time, the kinds of properties that become relevant in the description of dynamical systems are not only time sensitive, but also the scale invariant properties at both spatial and temporal dimensions. So we do need to have, and when we consider the interaction between these neurophysiological underpinnings and the computations that we're describing when doing syntax, the fact that the notion of time in derivational time is probably entirely orthogonal to whatever time dimension is is relevant for the description of a continuous dynamical system. So when we're describing syntax, for example, in terms of the complexity of a cellular automaton, which is what you were alluding to with Dave Medeiros' X-bar reduction, we can also ask, well, what are the trajectories that we're predicting for a particular model of phrase structure in terms of, is it going to have a linear growth? Is it going to settle to a finite set of metastable modes? Is it going to just go to chaos? And then what I think Doug is doing is providing information compression as a heuristic to choose what kind of structure building is empirically adequate if we want to model these operations, right? Because if you're just putting things together, then you have additive complexity in your structural descriptions. But it seems to be the case that if humans are sensitive to the distinction between additive complexity and fractal complexity, don't we want our structural descriptions to feature both? Right, so in that sense, I think that we have in our hands at least two interacting distinctions, one between scale-dependent and scale-independent phenomena at both spatial and temporal dimensions, and at the same time, additive complexity and fractal complexity in structural descriptions, which can lead, to an empirically adequate theory of syntax in the most traditional sense.
Mm-hmm. Well, thank you very much. Dr. Dari Moghadam, if you have any complimentary comments, we'll be very grateful to hear from you.
Thank you very much.
And you can switch your webcam on.
Okay, I try to do that also as well. Thank you. Well, I think that was a wonderful occasion for me to hear a lot of interesting ideas from the expertise who kindly accepted to participate in this session, in this biolinguistics session. And I'm very thankful to Professor Douglas Saddy for his very broad overview of the issues which he has been engaged in for several decades, or for decades, and integrating them. I think what we can conclude from this session, the biolinguistics session, is that there is a commonality that interaction is an important issue in understanding, in having a deeper understanding of what language is and how language works. And I think if that is the right assessment, then we have done service to the great audience that we have today. And I think as another positive aspect of this session, I can say that we had both the theoretical and empirical discussions. That is, some talks and presentations were more theoretical, theory-oriented. Some had a combination of theoretical and empirical, in fact, contribution. And that is important because the question of having an interactional model of language, in the sense that each one of us understands it to the extent that each one of us interprets it in his paradigm, then we have shown, I guess, to our addressees that this model can have a theoretical, in fact, a stronghold and background. So I think obviously an interactional model of language will not be an easy model of language. It should be a more complex model of language compared to the existing models of language, because it takes into considerations multiplicity of factors, which in an idealized situation, they are put aside. So there is a hard task before those people who work within such a model and the understanding that they have from this model. But I think we will have a more realistic understanding and picture of the essence of language, the components of language, and the autonomy of components of language, and the integration of them, interdependence of them. So we will have a more humanistic, rather than pure sciences, model of language. As humans have, I mean, there are many factors informing what our mind contains. So the model of language that we are investigating is expected to be a more complex model of language, because it's going to be a more encompassing model of language. And that is, I think, a very fruitful avenue of research. Thank you very much.
Thank you.
Okay. I'd like to take the chance here to express my utmost gratitude to our wonderful panelists. If, of course, my appreciation can ever cover the greatness of today, and it can't, it really can't. So let me see if I can activate my webcam. Okay, I can, very well. So with this, well, thank you very much, guys. It was just better than we thought it would be. We could write a novel about today, like literally, after finishing your book. So, and we've had participants from the very beginning until now from all around the world, I don't know, Nigeria, Europe, and so on and so forth, starting from 150 at least participants here. And to all of them, thank you very much. It's been, what a day it's been. So with this, we'd like to close. Any concluding remarks? Juan, Douglas, Diego?
I just want to echo very much what Professor Dabir Moghadam has said, because humanism is something we need at a time like the present, where you know, there was a report 2 days ago, I think it was in Nature or Science, that a group in Texas,
Nature. It was Nature,
was able to, or at least they claim, I haven't looked at the details of the paper yet, that they are able to get the basic structure of a linguistic thought in subjects through analyzing their brain. Now, this is either crazy as such, or maybe not so crazy given everything we're saying, but it could still be crazy if humans don't control that equation, because the last thing I would want is for any machine learning device to know what I'm thinking. So if we're giving ourselves the capacity to understand these issues, we have to be every bit as careful as we should have been when the atom was split. You know, but for the same reasons. I mean, ultimately, the survival of the species is at stake in us being all very responsible with what it is that we are analyzing. So I'll just leave it at that.
Okay, so let's hope for artificial intelligence not to be really intelligent. That's the ending of today.
Or for us to control it, what it is that it's doing. So, yeah.
Okay, well, but I actually believe in order for artificial intelligence to be intelligent, it has to have human language faculty, or it has to have some UG. Well, and I don't think when linguists don't know what UG is yet, and we don't know what language faculty is, machines are never going to get it. So let's go back to Chomsky and Descartes. let Elon Musk be happy. He's never going to get it. I'm a pessimist in this case. I may be wrong, but I hope not. Okay. Well, and by the way, there is a service link for the first panel of SOLAB conference here. You could, it won't take more than 5 minutes of your time. The participants, dear participants, please go and fill it out. And with all of this, I would like to close this session to look, and we're looking forward to seeing all of you in tomorrow's panels. Once again, thank you very much, guys, all of you.
Thank you. It was great.
Goodbye. Have fun. Have a great time.
Okay.